Hysteresis. What is hysteresis? That is, we have to define. The phenomenon of lagging of intensity of magnetization. The phenomenon of lagging of the total magnetic flux density or total magnetic field induction under bracket B, that is the magnetic flux density or intensity of magnetization of a ferromagnetic substance. Intensity of magnetization under bracket I of a ferromagnetic substance. Intensity of magnetization of a specimen of ferromagnetic substance, or material behind the magnetic intensity, that is H, capital H, behind the magnetic intensity, that is the magnetic field strength under bracket H of the external magnetic field in which the specimen is subjected to a cycle of magnetization. External magnetic field in which the specimen is subjected to a cycle of magnetization, is called hysteresis. The phenomenon of lagging of total magnetic field induction under bracket B, that is the magnetic flux density or intensity of magnetization under bracket I of a specimen of ferromagnetic substance behind the magnetic intensity, that is magnetic field strength under bracket H of an external magnetic field in which the specimen is subjected to a cycle of magnetization, is called hysteresis. When a specimen of ferromagnetic material is placed within a coil of wire carrying an electric current, the magnetizing field or magnetic field strength under bracket H caused by the current, magnetizing field or magnetic intensity under bracket H caused by the electric current forces sum of all the atomic magnets in the material to align with the field. We can divide four domains. We can divide ferromagnetic material or substance into four domains. This is a ferromagnetic substance in which there are four domains, and initially B0 is 0, that is external magnetic field is 0, magnetic intensity H is also 0, and these straight lines are atomic magnets which are aligned in this direction. That is, there are four domains in which atomic magnets are aligned in different ways. Atomic magnets are aligned parallel to each others, but alignment will be different in four different domains. And it occurs when external magnetic field of field induction B0 is 0, magnetic intensity or magnetic field strength H is also 0. These are atomic magnets, and vector PM or vector P is the dipole moment which acts from south pole to north pole. Vector PM acts downwards in this domain. atomic magnets of, and in this case these are the domain 1, 2, 3, 4, 1, 2, 3, 4, in which different atomic magnets are aligned parallel to each other in a definite domain, but do, definite domain. And atomic magnets, in this case atomic magnets are normally atomic magnets are normally oriented in different four different domains, are oriented in four different domains, and in a particular domain atomic magnets are oriented parallel to each others. And this occurs when no magnetic field, no external magnetic field or magnetizing field of field strength H acts on this ferromagnetic substance. Atomic magnets are normally oriented in four different domains when magnetizing field strength acts on it. When no magnetizing field strength acts on it, atomic magnets are normally oriented in four domains or four different domains when no magnetizing field acts on it. And in this case, external magnetic field B0 is 0 and magnetizing field H is also 0. And these are the direction along which atomic magnets are oriented in different four domains. And if an external magnetic field is applied, on this ferromagnetic substance, what will be the orientation of atomic magnets of this ferromagnetic substance? In this case, in the second diagram, an external magnetic field of field induction B0 and field strength H is applied on this ferromagnetic substance. Here, this ferromagnetic substance is placed an external magnetic field of field induction B0 and field strength H or magnetic intensity H. And in this case, all the atomic magnets in four regions will be aligned parallel to each other. Atomic magnets in this case will be aligned aligned in such a way that they are parallel to each other. In this way, atomic magnets are oriented in ferromagnetic substance, which is placed in an external magnetic field B0, and all the atomic magnets will be aligned in the same direction of the external magnetic field of field induction B0, and Pm is the dipole moment of each atomic magnet, and this Pm or dipole moment vector will be parallel to the external magnetic field of field induction B0 or magnetic field strength H. That is, vector Pm will be parallel to vector H or vector B0. If we repeat this point, that is, when a specimen of ferromagnetic material is placed within a coil of wire carrying an electric current, the magnetizing field under bracket field induction of B and magnetic intensity H caused by the electric forces sum of the atomic magnets caused by the electric current comma forces sum of the atomic magnets in the materials to align with the external magnetic field. When no external magnetic field acts, in that case, total dipole moment of the ferromagnetic substance will be 0. For the first case, when B0 is 0 and H is 0, in that case, total magnetic dipole moment of this ferromagnetic substance, that is PMT, will be 0. But when external magnetic field acts, in that case, total dipole moment, that is PMT, will be greater than 0. So here we can say that when the external magnetic field of field induction B0 is applied when the external magnetic field under bracket B0 is applied. B0 is applied by increasing the electric current, is applied by increasing the electric current in the coil. When the external magnetic field on B0 is applied by increasing the electric current in the coil, all the domains rotate till their magnetic moments, their magnetic moments of atomic magnets, till their magnetic moments of the atomic magnets are aligned in the direction of the applied external magnetic field B0 or H. The net effect of this alignment is to increase the total magnetic flux density or the total magnetic field induction or magnetic flux density B, full stop. And this aligning process does not occur simultaneously or in step with the magnetizing field or field strength H. This aligning process does not occur simultaneously or in step with the magnetizing field H, but it lags behind it. That means intensity of magnetization lags behind the magnetizing field H. In this case, along x-axis, magnetic intensity or magnetic field strength H, capital H, is plotted. That means in horizontal direction, magnetic intensity or magnetic field strength will be plotted. And I, that means intensity of magnetization, will be plotted along y-axis. I under bracket intensity of magnetization will be plotted along y-axis, and here I is equivalent to intensity of magnetization, which is plotted along y-axis, and B is equivalent to net magnetic flux density in the ferromagnetic substance. And this net magnetic flux density or magnetic field induction can also be plotted along y-axis. Now we can draw the graph along which intensity of magnetization or net magnetic field induction, that is B, will increase if magnetic intensity H is increased. This is the curve along which intensity of magnetization, that is I, will increase. This is the curve along which intensity of magnetization I will increase if magnetic intensity or magnetic field strength H is increased. Now I will decrease along this curve path. If magnetic intensity H is decreased, and finally intensity of magnetization increases to and saturation value in the opposite direction. Now we can complete the loop or hysteresis loop. This complete graph is called as hysteresis loop, in which intensity of magnetization or net magnetic flux density acting in ferromagnetic substance will lag behind magnetic intensity. We can denote different points of this graph. If H or magnetic intensity is increased from O to G, intensity of magnetization I or net magnetic flux density will increase along the curve OA and increases to the saturation point at the point E. That means at the point A on this hysteresis loop, H is equal to OG. H is equal to OG, or the value of magnetic intensity or magnetic field strength will be equal to H, which is equal to OG at the saturation point A on this hysteresis loop. And H is equivalent to magnetic field strength, or H. Now from the point A, we can draw a perpendicular on the vertical axis or on the intensity of magnetization axis, and that perpendicular is AL. In this case, AL is equivalent to OL, which is the value of intensity of magnetization at the saturation point, or this is the saturated value of intensity of magnetization of the ferromagnetic substance, or I is equal OL, which is also a value of intensity of magnetization at saturation point. If H is increased, I decreases along the curve AC. At the point C, H is equal to 0, but I has the value OC. I has the value OC. That means if intensity of magnetization or magnetic field strength is reduced to 0, then at the point C, the value of H is 0, but I has, or intensity of magnetization has some value, and I is equal to OC on this hysteresis loop, which is equivalent, which is called as retentivity, or the value of intensity of magnetization. The value of intensity of magnetization if H equal to 0, if magnetic intensity or external magnetic field is removed. And in this portion, the shaded portion on this hysteresis loop, that means OC is equivalent to retentivity. OC is equivalent to retentivity. And we can denote the retentivity or residual magnetism after removal of the external magnetic field of field strength H, or the net magnetic field strength retained by the ferromagnetic substance when external magnetic field is removed. Now, if H, or magnetic intensity, is increased from the point O to D in the opposite direction, in that case I, or intensity of magnetization, will decrease along the curve CD. And at the point D, I equal to 0, means intensity of magnetization decreases to 0. That means no pole strength will be retained by the ferromagnetic substance. If OD is equal to minus H, if an external magnetic field of field strength H is applied on this ferromagnetic substance in the opposite direction, and in this case OD is equal to minus H, negative sign of H, that means minus H indicates that in this portion magnetic field is applied in the opposite direction. That means magnetic intensity should be acted on the ferromagnetic substance in the opposite direction, and OD is equal to minus H, which is known as coercivity of this ferromagnetic substance, If H is increased in the opposite direction, in that case net magnetic flux density or intensity of magnetization will reach to saturation again. Here the point J is called saturation point when magnetic intensity is increased in the reverse direction. And also you can denote the point K and L, and if H is increased, and I will increase as according to the loop or graph, and this is the hysteresis loop. And we can consider the hysteresis loop again. If the intensity of magnetizing field or magnetic intensity is gradually increased from the point O to G, the intensity of magnetization under bracket I, or the net magnetic flux density or the net magnetic field induction under bracket B, acting in the ferromagnetic substance ferromagnetic substance bracket closed. The intensity of magnetization under bracket I or net magnetic flux density B rises to maximum value, rises to maximum or saturation value at the point E on the hysteresis loop. That means intensity of magnetization I or net magnetic flux density B rises to maximum or saturation value at the point A on the hysteresis loop at which all the atomic magnets in four different domains are aligned in the same direction of in the graph. If magnetic intensity H is increased from the point O to G, intensity of magnetization will increase along this curve OA, and A is the saturation point at which intensity of magnetization or net magnetic flux density acting in the ferromagnetic substance becomes maximum. When the magnetic intensity under bracket H of the external magnetic field of field induction B0 with respect to the ferromagnetic substance or specimen is diminished from the point G to the point O on the hysteresis loop. From the point G to the point O on the hysteresis loop, the magnetic flux density, the net magnetic flux density under bracket B or intensity of magnetization under bracket I. Intensity of magnetization under bracket I also decreases, but lagging behind the change in magnetic intensity, lagging behind the change in magnetic field strength H. That means intensity of magnetization I lags behind magnetic intensity H. In fact, when the magnetic intensity under bracket H has decreased to zero, at the point O, the net magnetic flux density B or the intensity of magnetization under bracket I of the ferromagnetic substance has a positive value at the point C. Intensity of magnetization I has the positive value at the point C when H is reduced to 0 at the point O. Therefore, at the point C on the hysteresis loop, H is equal to 0. That means magnetic intensity or magnetic field strength is reduced to 0, but I is equal OC. The value of intensity of magnetization I will be equal to OC, and this is called retentivity. Or residual magnetism of the ferromagnetic substance. I is equal to OC when H is reduced to 0, or magnetic field strength H is reduced to 0, which is called retentivity or residual magnetism. I equal OC, which is known as retentivity or residual magnetism or remanence, which is which is the value of magnetic flux density B, or intensity of magnetization, or the intensity of magnetization of the ferromagnetic substance. Intensity of magnetization under bracket I of the ferromagnetic substance. I equal OC, which is known as retentivity or residual magnetism or remanence, which is the value of net magnetic flux density B, or the intensity of magnetization I of the ferromagnetic substance after an external magnetic field of intensity H. An external magnetic field of field strength H is removed. On the graph, the magnetic intensity or magnetic field strength H is decreased from the point G to O, and at O H is equal to 0, and intensity of magnetization decreases from the point L to C. At the point C, I is equal OC. At the point C, I is equal OC, which is known as the retentivity, which is known as the retentivity of the ferromagnetic substance. The word remanence comes from, or is from, the two words remanent plus ence. The word remanence is from remanent plus ence. Remanent plus ence, meaning that is that which, meaning that which remains, The word is equivalent to that which remains. The word is from the two words remanent plus ence, meaning that which remains, and which is equivalent to remanence, From the point O, as the strength of magnetic field, under bracket H is increased in the opposite direction. As the strength of the magnetic field H is increased in the opposite direction, that is along OD on the hysteresis loop. As the strength H is increased in the opposite direction along OD on the hysteresis loop, the intensity of magnetization under bracket I, or net magnetic flux density acting inside the ferromagnetic substance, the net magnetic flux density under bracket B of the ferromagnetic substance decreases, that means reduces and becomes zero, at the point D on the hysteresis loop. Therefore, at the point D, I equals 0 means intensity of magnetization will be 0, and minus H is equivalent to OD. Which is known as the negative value of magnetic intensity or magnetic field strength H is equivalent to OD, and which is known as coercivity of the ferromagnetic substance. Minus H is equal OD on the hysteresis loop is known as coercivity of the ferromagnetic substance, which is the value of magnetic intensity or magnetic field strength under bracket H, or the magnetic field strength of magnetizing field H applied in the opposite direction, due to which what becomes 0, Minus H is equal to OD on the graph, which is the coercivity, that is the value of magnetic intensity applied in the opposite direction to reduce the retentivity or residual magnetism of the ferromagnetic substance to zero. Ferromagnetic substance to zero. Coercivity of the ferromagnetic substance, which is the value of magnetic intensity H or strength of magnetizing field H applied in the opposite direction to reduce the retentivity or residual magnetism of the ferromagnetic substance to zero. On the graph, D is the point at which intensity of magnetization, that is I, reduces to zero from C to O. I is equal to zero, or intensity of magnetization will reduce to zero at the point D, and minus H is equal to OD. This portion OD is known as coercivity. The portion OD on the hysteresis loop is known as coercivity, or the value of magnetic intensity H, due to which value of magnetic intensity H applied in the opposite direction to reduce the retentivity or residual magnetism of the ferromagnetic substance, which is known as the coercivity. A further increase in magnetic field strength H or magnetic intensity H. Further increase in the magnetic intensity H in the opposite direction. Further increase in the magnetic intensity H in the opposite direction from the point D to J, from the point D to the point N, comma, causes the magnetic flux density, net magnetic flux density B, or the intensity of magnetization under bracket I acting in the ferromagnetic substance. Further increase in magnetic intensity H causes the magnetic flux density B, or intensity of magnetization I, to reverse and finally reach the saturation point. Again, when all the atomic magnets are completely aligned in the opposite direction of the applied magnetic field. As the magnetic intensity H is increased from D to N in the opposite direction, the intensity of magnetization increases from the point D to J along the curve path DJ, and at the point J, I reaches to the saturation value. Intensity of magnetization reaches to saturation point in the opposite direction. So another point to discuss in this topic, that is the cycle may be continued so that the graph of the flux density under bracket B lagging behind the magnetic intensity H or the magnetic field strength H. The cycle may be continued so that the graph of flux density B lagging behind the field strength H appears as a complete loop, known as a hysteresis loop.